Welcome to a video on section 6.2 regarding the indefinite integral and anti-differentiation using substitution. So this section should reinforce some of the stuff we've done previously with antiderivatives as well as integration. Well, they're pretty much the same thing, but it will reinforce what we've done recently. So what we're first going to talk about is a definition of an indefinite integral. So when you see the word indefinite, basically means it's not definite, right? So it's not really well defined, or basically without limits. So the answer will be an expression instead of a number. And you'll see what I mean by that when we start working through these examples. We write an indefinite integral in this way. So again, no limits. So there's no like lower or upper limits. And if we just think about FTC, or fundamental theorem of calculus again, capital F being kind of like the antiderivative, if you take the derivative of that, you get back to the original function. So think of that as like antiderivative, because it seems as if we do the indefinite integral of f of x, little f of x, we get capital F of x. And of course, there's a constant of integration. So if I look at like example 1 here, what would be the antiderivative of e to the 3x? Well, it's going to be e to the 3x, but we're also going to be divided by 3, because if you take the derivative of e to the 3x over 3, you get back to e to the 3x using chain rule. And of course, the plus c. And remember our chain rule bit, if you take the derivative of e to some exponent, it's going to be e to that exponent times the derivative of your exponent, or in this case we're calling it u. If we look at some other situations here, like if I take the indefinite integral of 3x squared, it's x cubed plus c. And we call that a family of functions because there's a whole bunch of functions that can represent the antiderivative of 3x squared, like x cubed plus 1, x cubed plus 10, x cubed plus a million, x cubed plus 2.435, whatever, 8. Any number you can think of. Of course, this is a definite integral right here, because, again, I have x cubed, I'm integrating from 1 to 2, so I substitute 1 and 2 and take the difference, and of course I get 7. So this gets us a answer, a numerical answer. And then if we look at some of these other scenarios, like 1 to x of 3x squared, or 3t squared, 3r squared, or 3s squared, basically you're taking the antiderivative of any one of those expressions. Let's say we focus on 3t squared. So it's t cubed from 1 to x. And of course you substitute, get x cubed minus 1. And that's basically a function in terms of x. So hopefully you kind of see the difference of some of these. Like if you don't see any limits, just an answer. I'm sorry, it's just an expression. If you see limits, it's a numerical answer. If you see something like from 1 to x, then it'll be a function in terms of x, I guess, with no constant. And we consider this to be area accumulation. Kind of like what we had on our last test, which you guys have fond memories of. That's a joke. Okay. So, again, that was a joke. So, let's go over here. Hopefully you remember when we have a constant, we can pull to the left. So the same property still applies to indefinite integrals like we have for definite integrals. If you're adding or subtracting two functions, you can also break it up. That's something you guys kind of forgot to do in our last test, so make sure you remember to do that. If f of x equals this, and you take the derivative of it, do remember that we got to do a product rule. So we're kind of going back to first semester stuff here. If I do a product rule, that's going to be 1 times ln x minus 1. So basically ln x minus 1. And, oh shoot, hold on. I really screwed that one up. I forgot to do first semester stuff. Okay, so you take derivative of x times ln x, then plus x times 1 over x, and then, of course, the derivative of negative x, which is negative 1. So you get ln x plus 1 minus 1, which, of course, is ln x. So what this tells us is that the antiderivative of ln x, which we haven't really talked about yet, is actually x times ln x minus x, and plus c, of course. Now, if you look at this next one, with y equaling ln of absolute value of x, remember you can break it up as a piecewise function. We have absolute value. Of course, the first function is when x is greater than 0, the next one when x is less than 0. So if I take my derivative with respect to x, I have 1 over x, but then I get 1 over negative x times negative 1 using a chain rule, which of course would be back to 1 over x. So this tells us that the antiderivative of 1 over x is natural log, which we would expect, but you gotta say absolute value of x, so plus c. So that's very important. And also remember that the derivative of natural log of absolute value of x is just going to be 1 over x. However, the derivative of natural log of x without the absolute value is 1 over x, with x being bigger than 0. So you can't log negative numbers, so just kind of keep that in mind. But if you have the absolute value, it's kind of implied that x is already going to be bigger than 0, so you don't need to say anything about that. Okay. Oh, another thing too is that if I take the antiderivative of 1 over x times dx with the condition that x is greater than 0, then of course you can say natural log of x plus c and don't worry about the absolute value. But if you don't include that, then we have to go with this, with the absolute value. Power formulas, which you guys should be pretty comfortable with. So we know the derivative power formula, which is n times x to the n minus 1. But for antiderivatives, it's going to be x to the n plus 1 over n plus 1 plus c. We kind of talked about that already. N cannot equal negative 1, otherwise you're doing log, or natural log. So that's what we see here again. For trig, kind of go through these kind of quickly. That's sine x plus c. The other one's negative cos x plus c. That's tan x plus c, secant x plus c. That's going to be negative cotangent x plus c, and of course, negative cosecant x plus c. Inverse sine of u plus c. Inverse tan of u plus c. And inverse secant of u plus c, because the derivatives of those will get you back to what you see in the integrand. E to the x plus c, now we know that's going to be x ln x minus x plus c. These here are a little interesting. We need 1 over ln a times a to the x plus c, because if you take the derivative of that, you'll get back to a to the x. And this one's going to be 1 over natural log of a. Actually, this one's a little bit funky here. Why am I going blank on this one? This one I should know. Actually, yeah, it's going to be 1 over ln a times x ln x minus x, and of course, plus c. The reason why, sorry I went a little blank on this one, is you can do a change of base formula. So log base AX can be written that way. And that explains why I can pull that ln A off to the left, and then focus on anti-deriving ln X. Okay, last example, then I'll end the video. So if I'm anti-deriving f of x, basically it's x cubed over 3 plus x plus c. That's all I have. For this one, now I replace x with u. So it's u cubed over 3 plus u plus c. And I did this with respect to with u, because you see the du there. Very important. But then this one, they're different. So it's really it's f of x cubed times dx, which is going to be x to the 6 plus 1 times dx, because I've got to replace x with u, and u is x cubed. Now if I take the antiderivative, I have x 7 over 7 plus x plus c. So the moral of the story is to pay close attention to du and dx, because it does kind of guide how you're going to do the antiderivative. And we'll talk more about that when we do page 3 and 4 of the notes in class next time. Okay, that concludes all the notes here.